Hi everyone, my name is Li Xinyuan. I'll be introducing JHU HLTCOE submission to the VoicePrivacy Challenge 2024. Names of my wonderful collaborators are shown here. For a quick recap, the goal of the VoicePrivacy Challenge is to remove as much of the speaker identifying information from each utterance as possible, while attempting to preserve as much of the content and emotion of the original utterance as possible. Reconciling the two somewhat conflicting objectives is a non-trivial task, as we can notice that most baseline systems are strong in one of the two challenge objectives, but not both. Our initial focus was to build systems that outperform baseline systems in one of the two evaluation categories, privacy or utility. As such, we came up with two initial approaches. The first one, the KNN-VC system, is a simple system aimed at preserving more of the source signal, especially the emotion aspects, similar to the baseline system based on the McAdams coefficient. We were able to achieve better emotion preservation with a KNN-VC system than any of the challenge baselines. Our second approach, the cascaded ASR and TTS system, primarily addresses the privacy objective, achieving a strong equal error rate of nearly 50%. Having built systems that excel at each of the two challenge objectives, we next propose a straightforward yet effective method which excels at both objectives, randomly choosing from one of our two aforementioned systems at utterance level. By controlling the chance of each utterance being anonymized with one of the two above-mentioned systems, we can effectively control the degree of priority that we give to the two objectives. With this system, we achieved emotion preservation performance comparable to that of the best emotion preservation baseline, while simultaneously getting similar equal error rates to the strongest anonymization baselines provided by the challenge organizers, namely the ASR-BN system. We'll now delve deeper into our three systems. First, let's look at the KNN voice conversion system, adapted from work by Bas Italia in 2023. In this system, we first extract a matching set, a set of waveform feature frames extracted from utterances by one or multiple target speakers. Then, at inference time, we first convert the input waveform into a waveform feature sequence. For each frame in the input waveform feature sequence, we perform KNN regression to identify the k-nearest neighbors of set frame within the matching set of each target speaker, respectively. We then pull together the k-nearest neighbors of set frame from each matching set in some fashion, such as deploying a simple numerical or weighted average. The resulting pooled KNNs form a converted waveform feature sequence, which can then be vocoded into the output waveform. The KNN-VC system should be noted for its simplicity. It does not require the training of any new neural models, although the original authors did suggest retraining a vocoder, the benefits are marginal. Qualitatively speaking, KNN-VC is very strong at capturing the voice characteristics and the acoustic environment of the target speaker, owing to the rich expressiveness of waveform features. However, due to the strict frame level alignment between the input and output waveform feature sequences, much of the source speaker's identifying characteristics, such as accent or speech rhythm, propagate through into the converted utterance. As such, the anonymization performance of the KNN-VC system is quite weak. Next, we will look at our cascaded ASR and TTS system, which targets the anonymization baseline. We first perform ASR using Whisper, one of the strongest ASR models available to us. We subsequently perform TTS using VITS, with Whisper's outputs as input text, and targeting a randomly selected speaker from libTTS. By bottlenecking the input utterance into the text space, we can very effectively remove any identifying information other than the speech content. Therefore, this system achieves an outstanding equal error rate of nearly 50%. However, as VIT does not support emotion-controlled TTS, our cascaded ASR and TTS system is worse at emotion preservation than any of the challenge baselines. Having described our first two systems, which each stands out in one of the two objectives of the challenge, we proceed to introduce our random admixture system, which, for each utterance, we choose one of the two systems that we just described at random. The probability of each utterance being converted using the TTS system versus the KNMVC system acts effectively as a slider with which we control how much we would like to focus on privacy use versus utility. Due to the way the adversary is set up in the challenge setting, where ASV evaluation is performed using a model trained on anonymized data, the ASV model is vulnerable to data poisoning attacks, where the model fails to learn a good decision boundary due to the difficult nature in learning the underlying distribution. As a result, the equal error rate of the random admixture systems are better than the weighted averages of the equal error rate of the individual systems. On the other hand, due to the fact that the evaluation for utility metrics is performed using pre-trained models, the UAR of random admixture systems are exactly the weighted averages of the UAR of the individual systems. As such, instead of the privacy utility trade-off line being the pink line on the diagram, we observe the more favorable orange line on the diagram in our experiments. This concludes our presentation. Thank you so much for your time. Our complete results are shown in this table and can also be found in our paper. Please direct any questions to my colleague Matthew. Thank you.